Okay, so we're going to talk about continuity and limits. Right? Specifically, how we're going to use limits to determine continuity. Right? Clever. All right. So what's this? So which functions, right, are discontinuous here? Right? And if they are discontinuous, where are they discontinuous? So what does it mean to be discontinuous? So let's actually start the middle. So you can see I have the function doesn't exist left of -2. So once it starts existing, right, then it's all continuous. It's all nice connected dots, connected until I get to this gap. So this would be a discontinuity. All right. So to be continuous, I need to be able to draw the function, without picking up my pencil, right, or pen or whatever it is. So here's the gap, and the gap occurs at 2. So this would have a discontinuity at 2, right? X equals 2. Well, same thing here. Here I'm all happy, 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 happy until I get to -1. Then I have to jump up and start the graph again. So this is also a discontinuity because it breaks the graph up. All right, so there'd be a discontinuity here at x equals -1. So if we go to the other one, notice that I can just follow this whole graph. There are no breaks, there are no jumps, there's no gaps, there's none of that. So this is just continuous. All right. Okay. So you want to stop this and do class work problem number 1. All right, let's do a little limit review. So now this is going to be the key to understanding what's going to come next. So let's remember that if the limit exists, it means that the graph is going to connect at this y value around this x value, right? Okay, and so remember that f of -1 means this is the y value at that x value. So let's start with the left part. So since the limit exists and the limit is -2, I know that the graph has the same behavior around that x equals -1, and that behavior is -2, so it's going to connect at -2. So I know this graph connects at that y equals -2. I don't know if it's an open circle or closed circle, right? Defined or undefined point. Well, that's what the next part tells me. F of -2 equals 2, I know it's a defined point right here, and I know that these two y values are the same. So not only does the graph connect, it connects at a closed circle or a defined point. All right, next. So again, now I know that the graph connects at y equals 1, right? Because remember, the behavior around x equals 2 will be y equals 1. Okay, now the actual point is undefined. So I know it connects, but it can't connect at a defined point. It's got to connect at an undefined point, which is an open circle. All right, so now if you think back to what we did in the slide before, that means that this is a discontinuity, right? I have a graph that connects, but it connects at an open circle, a gap, all right? Okay. So last one, I have the limit as f, or the limit equals infinity. So I know the two sides left and right will go to infinity. Well, that doesn't connect. They just shoot off to infinity. And in fact, that makes sense why there's an undefined point, or all the y values are undefined at f equals -3, right? Because there's going to be a vertical asymptote here. Right? And I didn't show that in the examples before, but that would be a discontinuity as well, right? The graphs do not connect. Right? Okay. So with all that, let's go through all our stuff. So this is what's going to be called a point discontinuity. So here's my graph, and notice it's discontinuous because as I've come along, and it's continuous all through the solid part until I get to A. And then there's a big gap there's a point gap, right, in the graph. Now, it doesn't matter there's a closed circle up here. It only matters that I can draw the entire thing without picking up my pen or pencil, and I can't because there's a hole here. All right, and I'll do, after this slide, I'll get rid of this point, and you'll see I can still figure out that it's a point discontinuity. All right? Okay, so now, how do we figure out what it is, what type it is, using limits? Well, first thing is, I know f of a exists because I have a closed circle, so that's okay. And the second thing is, I'll do the limit. And I know the limit exists because, right, it has the same behavior. It connects at an open circle. So remember, a limit will have the same behavior around this x equals a, which means it has to connect at whatever that y value is. Well, the graph connects and the point exists, but notice they're not the same. Where the point exists and where the graph connects are not the same, so this has to be an open circle here. That's what tells me that it's a point discontinuity. So here's the key. It's the fact that the limit and the actual y value of the point aren't the same that this is the visual, right? It's got to be a closed circle somewhere and an open circle on the graph. That means point discontinuity. Okay, and that's the key. This red part's the mathematical proof that this is a point discontinuity. All right, so what if I got rid of that point? Well, you can see it's still a point discontinuity, right? There still is one point in this graph that, is gone. That's the gap. The gap is a point. Well, in this case, it would be the actual y value does not exist, but that's not enough to tell me that it's a point discontinuity, because remember, it could be a vertical asymptote. So then when I figure out the limit exists, so now that I know the limit exists, I know the graph connects. And since the y value doesn't exist, I know it connects at an open circle. So those are my two variations on point discontinuity. All right. Okay, let's do jump discontinuity. So a jump would look like this. And, there's literally a jump in the y. So if I start from the left and go up here, I have to jump up to the y to continue my graph. If this were down, I'd have to jump down and continue my graph. Well, how can I tell mathematically that this is a jump? Well, the point would exist. And again, it doesn't really matter. This could be an open circle. All right. But in this case, this point exists. But now the limit doesn't exist. All right. So since the point exists, I know it's not a vertical asymptote. And then since the limit doesn't exist, I know that it doesn't connect. It has to be a jump. All right. So these two things in combination will mathematically show me that it's a jump discontinuity. Okay. Now, infinite discontinuity. Well, it's got the word infinite in it, so it's probably going to go to infinity somehow. Well, this is one version. So now notice there's a vertical asymptote at x equals a. So what do I know here? I know the actual y value. So f of a does not exist because it's a vertical asymptote. And then I know the limit actually goes to infinity. So as soon as I see does not exist in combination with the limit is infinity, I know there's a vertical asymptote here, and it's an infinite discontinuity. Okay, what are my other choices here? Well, they could also point down. So if both the arrows went to negative infinity, I'd still get the function doesn't exist at a, and I would get that the graph or the functions go to negative infinity. That's what the limit tells me. All right, and then what's my last version here is they could both go in different directions. So I know that the function doesn't exist today, again, vertical asymptote, and then the limit doesn't exist. All right, so it's in conjunction with these two that I know this is going to be a vertical or an infinite discontinuity. All right, okay. Okay, so now what if it is continuous? Well, if it's continuous, then I just have nice solid line, no gaps, no jumps, no breaks, no nothing. All right, and you can see at A, the actual y value exists. In fact, here's the y value. The limit exists. You can see they both connect at this y value. So here's the definition, and this is what we use for continuity in calculus, is if the limit exists and that limit's the exact same thing as the y value at a, then it has to be a nice continuous graph. Right? There can't be a jump, a break, a gap, anything, because the behavior around a will be the same y value as the point. All right. Okay. And so in all of this, like I said, we're getting into calculus, so it's abstract in a way, but it's very conceptual. So this is not an easy process. So having said that, what we're going to do is all we do is state this continuity limit. That's our definition. And by default, we'll use this concept, which implies all the other discontinuities. All right. So when we see it, here are our discontinuities, right? So if I have a point discontinuity, remember, this point doesn't have to exist, but here's the gist of it, right? The graph connects, that's the limit exists, but it doesn't connect at the closed circle point, so these two are not the same. All right. If they were the same, this closed circle would be over this, and that would be continuous. All right. So that's how we figure out a point discontinuity. We calculate the limit, we find the y value, and see if they're the same. Okay, a jump. Well, oops. So a jump, okay, I can't stop this. So a jump, right, the y value exists, right? And again, it might not exist, but it would change this just a little bit. So let's say it exists, but then the key here is the limit doesn't exist. So when the limit doesn't exist, it means that the graph doesn't connect. So I know the graph doesn't connect. I know there is a y value, so it can't be a vertical asymptote. These two together imply jump discontinuity. All right, and then our last one. Well, there's a vertical asymptote, so the actual y value can't exist. And then the limit will either be plus infinity, right, if they point up, minus infinity, or negative infinity if they point down, or if they point in different directions, it won't exist. So those are three options right there. And all of these in conjunction will tell me it's an infinite discontinuity. All right. Okay. So let's stop this and complete class or problem number 2. All right. So now let's do a couple problems. So I want to identify each discontinuity. All right. And then I want to show mathematically that it is that type of discontinuity, right? So if I say it's a point discontinuity, I want you to show me mathematically that that's true, right? If I say infinite or a jump, prove it. All right. Okay. So I'm going to start at the very left here. And you can see it's all continuous, 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 continuous until I get to this point. That's my first point of interest, and that's right at x equals -7. Well, I want to see, from the graph, I know that it's a single point. This is a point discontinuity. So I know it's a point discontinuity, x equals -7. But now let's prove it. Okay, how do I prove it? Well, I find the y value there. Turns out the y value doesn't exist. And then I find the limit there. So the limit is 1.5. Okay, so the fact that the limit exists means the graph connects. The fact that the point itself doesn't exist means it has to connect in an open circle. So these two things together prove to me that it's a point discontinuity. All right. Okay, let's go to our next one. So you'll notice it's all continuous, continuous, continuous until I get to -5, and then I have something weird. And it looks like they go to infinity, right? It's a vertical asymptote. So this is an infinite discontinuity at x equals -5. And now let's prove it. Well, the y value at 5 or -5 doesn't exist. That's my first step. And then my second step is to do the limit. Here, the limit doesn't exist. So in conjunction, these two tell me that it has to be a vertical asymptote. All right. Okay, so let me just make a confusing point right here. If we had a jump where both of these were open circles, it would technically fit these, all right? But we're not going to do that at this stage. So any jump will have a closed circle somewhere, a defined point. Okay, so if you see that the function doesn't exist and the limit doesn't exist, that's going to be infinite, all right? All right, even though it's a little bit of a misnomer. All right, then let's keep going. So here I have continuous graph, continuous graph, continuous graph until I get to -3. That's my next point of interest. So you'll see at -3, it looks like a jump. So I'll say a jump discontinuity at -3. Now let's prove it. Well, the y value is 2.5 at -3. The y value is 2.5. The limit does not exist because the graph doesn't connect. So these two things in conjunction tell me that the graph doesn't connect, but there is a y value, so there's not a vertical asymptote. So in conjunction, this lets me know there's a jump discontinuity. All right. Okay, we'll do one more. So again, all continuous, continuous, continuous till I get to x equals 0. So this again is one point that's gone. So this is a point discontinuity at x equals 0. Well, let's prove it. So f of 0 is -2, so the y value exists at 0. The limit exists. Oops, this should be a 0 here. So let me fix that just real fast. So this should be a 0, not a 90. This should be a 0. And okay, so the limit at x equals 0, or as x approaches 0, does also exist. But now the fact that these two are not the same means that it has to be a point discontinuity. Means the graph connects, but it doesn't connect at the closed circle, right, the defined point. All right? Okay. So let's stop this, and you want to do classwork problem number 3. Okay, let's do some notes here. So remember before, I talked about continuity. So we're going to use this definition. So this is called the continuity test. So a function is continuous at x equals a. And if you ever see IFF, it just means if and only if. So this has to be true, right? So this is true. It's continuous if and only if this bottom part is true. And here's our definition, right? So if the limit of f of x as x approaches a equals the same y value at a. So this tells me the graph connects. The fact that it equals this y value tells me it connects at a closed circle. All right, that's the definition we use. And then again, by default, if I screw any of this up, if any of this isn't true, then it's got to be discontinuous. And based how it's, untrue, that will tell me what type of discontinuity. Okay, but this is the definition we use. And then we kind of use logic to play off of this. All right, and again, how do we do that? So note, well, if the limit exists and doesn't equal the y value, then there's got to be a gap in the graph, a point. So that's a point discontinuity. If the point exists but the limit doesn't exist, then that has to be a jump. And then if the point doesn't exist and the limit either doesn't exist or goes to positive or negative infinity, so that should be added here, so positive or negative infinity as well, then it's got to be an infinite discontinuity. Okay, so if this is true, it's continuous, but if it's messed up in any one of these three ways, that tells me the type of discontinuity. All right. Okay, so let's try one. Let's determine whether this function is continuous at this point. Okay, if it is discontinuous, I want to know the type of discontinuity. Well, what's the key? And here's the key concept, so we should write this down somewhere, right? I only need two things to figure out if it's continuous. I need the y value at -1, and I need the limit as I approach -1. So let's start with the y value. The y value is easy. I just substitute x equals -1 in, and I'll get -4. So at x equals -1, y is -4. Now let's find the limit. So let's do our table. I want the limit as I approach -1. So let's do our standard, subtract off 1,000th, 100, or 100th, a 10th. Let's add 1,000th, add 100th, add a 10th. And then we're just going to plug those x's into this function. And then we can see as I come in from the left, I approach -4. As I come in from the right, I approach -4. The limit is -4. Okay, so this tells me since the limit exists, the graph connects. And since the y values are the same, the graph connects at a closed circle. This is a continuous point. All right, so because those two are the same, the graph connects, and it connects at a closed circle, a defined point. It's continuous. All right? All right, and so now there is no discontinuity because it's continuous. All right, let's do the next one. So here I have x squared minus x, the whole quantity divided by x, and is it continuous at x equals 0? Again, key concept here is I need two things. I need the y value at 0, and I need the limit at 0. Well, the y value at 0, plug in 0. You're going to get 0 over 0. Since there's a 0 in the denominator, this y value is undefined. All right, so the y value doesn't exist at x equals 0. Well, let's do the limit now. So 0 is my point of interest. So again, subtract off 1,000th, 100th, a 10th, add 1,000th, add 100, add a 10th, plug them in. You can see as I come in from the left, I approach -1. As I come in from the right, I approach -1. So the limit is -1. Okay, so now this tells me that the graph connects at y equals -1, but at x equals 0, there are no defined y values. So this has to connect at an open circle. So this has to be a nice connected graph just with one point gone. So this is a point discontinuity. All right. Okay. So that's actually the end of the video. So you want to stop this and just finish the class.